So I actually did about a third of what I had prepared. I knew I had prepared too much, but I can, if I don't complete it here, I'll continue anytime that seems appropriate. I can continue on Friday as needed. So I described something from that paper of Yves André, a very beautifully written little paper about which I'm by no means an expert, on how the classical Durand theorem, together with Grothendieck's theorem about rational forms, rational versions of Grothendieck's theorem about rational forms give you a whole bunch of very interesting numbers which are not rational, which in fact are conjectured to be transcendental, or at least many of them are. And it seems a beautiful construction, but nonetheless, I did mention that it's not ideal as it stands, because algebraic varieties contain all kinds of internal information, and to just say that you get a matrix of elements of order equal to a given homology group, a square matrix of size equal to the given homology group, really nice as it is, doesn't leave you too much room for, appear to leave you too much room for further stuff. But I'll just say, I think I said it this morning. So let's call this, I don't know if this is fair to call it a dream, but I think it probably was. Separately, Grothendieck and Langlands. Separately and with different emphases. Construct universal groups. GF, motivic, this would be the motivic Galois group, and LF, this would be the automorphic Galois group. That together would one would govern, I don't think this is too much of an exaggeration to say this, would govern the inner structure of varieties over Q. You really, if periods are gotten from these varieties and from the cohomology of these varieties, it would be very nice if you could have something that would get inside them and give you more information about them. And two, and this I think I defer to Sasha, but it seems that one might expect express all periods, well, I don't know whether all is fair, periods, in terms of corresponding L functions. L, S, R. For finite dimensional representations, of the motivic Galois group. Well, we'll see presently that, so R is a representation. So the motivic Galois group, GF, that's set up by Grothendieck, that's an algebraic group, actually a pro-algebraic group because it's got infinitely many simple factors. So it's a reductive pro-algebraic group. And what you want is a representation of that into GLNC. And that's great. That would be great. That was why Grothendieck invented this. Well, it was one of the several reasons that he in his mind constructed this group as a consequence of several really quite difficult axioms, which to this day I think remain not entirely proved. And then Langlands, so that would be very good to have this, but even so, this is not all that, we'll see, but it's not all that concrete. It's a group that does govern the inner structure of the cohomology of algebraic varieties, but it's given by rather abstract, according to Grothendieck's axioms, involving categories, basic properties of categories, Tannakian categories with a fiber functor. It's pretty abstract, but and then I guess the contribution of automorphic representations is to give a way of writing this down that is more concrete. Whoops. So Langlands proposed, Grothendieck proposed this, I don't know, in the 1960s possibly. Langlands proposed this group in 1977 in the Corvallis conference. He had this as a huge pro-algebraic group, and together with a homomorphism, surjective homomorphism. I won't write it surjective here, but he had a surjective homomorphism of this pro-algebraic group into this one, which wasn't as big, was more manageable. It was pointed out by Kottwitz that a little while later that that's really not the right way to think of this. Langlands' theory of automorphic forms is a theory of analysis, and a theory, I mean, even though it governs all kinds of things in arithmetic geometry and number theory, it's a theory of analysis. It's spectral theory. It's the, as we noted this morning, it's the spectral theory of Laplace-Beltrami operators, and I guess perhaps they're sometimes called momentum observables, operators that commute with the Laplacian, but in this case they're parametrized by prime numbers. So it's more concrete with these conjugacy classes. But it should be regarded, as Kottwitz pointed out, as a locally compact group. This is a complex. Well, the way it's more than what I'm about to say. The construction conjectural construction I will talk about is of this thing as a complex group. It really should be a complexification of a group defined over the rational numbers, actually. But anyway, as a complex group, you can certainly talk about a homomorphism of a locally compact group into a complex group. That's exactly what's going on when you think of the dual group and the L group of Langlands. In any case, this is, I'm writing a Latin letter for a locally compact group, and I'm writing a script letter for a pro-algebraic group. As it happens, this G would, let's say this stands for Grothendieck and that stands for Langlands. So this is the best thing to have. You want both of these things. These things govern periods, but then you want something more concrete, and that would be governed by a piece of this thing. This is not going to be, there's going to be definitely a kernel of this thing. What's in the kernel is very poorly understood. If we understood that better, we'd perhaps be closer to proving functoriality. But nonetheless, one can describe what the kernel should be. That's not the issue, but the part of it that actually is not in the kernel and goes to here governs motives. So that's what one should be asking for. Questions or any comments? All right. So let's say on the automorphic, we'll do the automorphic Galois group. Probably all I will have time for today. LF, and I'm not going to give all of the details of this, but but in order to put it into perspective, as a locally compact group and as a group that therefore somehow governs spectral phenomena, it takes its place in a much better known collection of locally compact groups. So let me just review what those would be. We've got Galois groups. Okay, so I'll write Galois group of F, the Galois group of F bar over F. So that's the inverse limit over finite Galois extensions of finite Galois groups. It is, so it's a compact, large infinite, but compact and totally disconnected group. That's the Galois group. I just note that Galois group of E over F, this is an aside, it comes with a family of conjugacy classes parametrized by unramified primes of F unramified in E. So a family let's call them the Frobenius conjugacy classes V, sometimes written script F, V. These are conjugacy classes sitting in this Galois group, parametrized by unramified primes. And in the way we've been describing it, that is to say primes outside a certain finite set of primes. Those are the Galois groups. Slightly more elaborate than them are the Weil groups. So I'll say on another occasion, describe how Weil group, I really haven't understood them properly, but not that they're not rocket science by any means, but there's a very complete article on Weil groups by Tate. It's his the first article in volume 2 of the Corvallis Proceedings. But he takes no prisoners, and it's I mean, the Weil groups are not like the Langlands group or anything like that, but they're someday I should just sit down and do nothing else for a couple of days and understand properly Tate's article. But in any case, Weil groups are closely related to abelian class field theory. They're in fact, if sort of one looks at it properly, they are just natural consequences of abelian class field theory. So I'll try to describe that on another occasion. But in any case, the Weil group This comes from the finite extensions, the Weil group of E over F, so it's like the Galois group, it has a universal version that's over the algebraic closure. And so just like the Galois group, this is an inverse limit over finite Galois extensions of a Weil group, a relative Weil group. And this is, again, a locally compact group. These are Galois extensions. And it's a locally compact group. And it comes with a homomorphism, a surjective map, as a matter of fact, continuous homomorphism from the Weil group onto the Galois group. So we will we'll go back. I've been discussing individually the 7 questions that were in Langlands' article. He didn't want them referred to as conjectures. He said they were just questions. And we've been going one after the other of 7 questions. The last 2 questions, 6 and 7, concern Weil groups. They were very new at the time of Langlands' Bochner article, and they gave more information about automorphic representations, conjecturally at least, as groups that could be used conjecturally to describe automorphic representations. That group basically would describe parameters, things of homomorphisms that parameterize automorphic representations, but by no means all of them, but more than what you would get just by taking the Galois group. All right, so the third thing then is the Langlands group. This is conjectural. And so it just fits into this sequence nicely. Once again, it's a hypothetical. The only thing that's different is this is hypothetical. It's a hypothetical locally compact group. Much bigger than the Weil group. The difference in size between the Langlands group and the Weil group is much larger than the difference in size between the Weil group and the Galois group. But nonetheless, hypothetical, locally compact group, homomorphism. Continuous homomorphism, surjective. And this one, unlike the Weil group, this one would classify, it's supposed to classify all automorphic representations. The Weil group, questions 6 and 7 actually, we're talking F as the global field here, but question 7, the last question of Langlands, was about the Weil group and how, the global Weil group, and how, question, does homomorphisms of the global Weil group into the L group, which we defined this morning, do they classify, do they give automorphic representations? He knew right at the time they wouldn't give them all, but they would give more than just homomorphisms of the Galois group into the global L group. And I just say, I mean, from earlier lectures, I'll just say as an aside that homomorphisms of the Galois group into the global L group, that's the smallest collection. Well, we've got 3 locally compact groups. This one's actually compact. This is locally compact. This is locally compact with surjective homomorphisms. And part of Langlands, I'm repeating things, but part of Langlands' theory was that he gave a very convincing argument, basically as a special case of functoriality, that homomorphisms of this into, I'm going to write this down, I'll write this down. I'm not going to leave it on the board because it's not part of the flow of this, but homomorphisms from the Galois group into the L group. These would the conjecture that these things should give rise to automorphic representations is non-abelian class field theory. In other words, the the conjectural fact that a homomorphism, or just think of this even as the general linear group, the homomorphisms of the Galois group into the general linear group, that is to say representations of the Galois group, this compact, totally disconnected group, maps of this into the complex general linear group. Part of functoriality, I didn't go over it today, but we've talked about it in early lectures. Part of functoriality is that these things classify automorphic representations and therefore attach automorphic representations to purely Galois theoretic data. Homomorphisms of the Galois group into here. This is the group you want to understand. This is the group you want to classify. You want to classify Galois extensions of the rational numbers. Abelian class field theory, as I've said before, it basically tells you that abelian extensions of this correspond to it characterizes abelian class field theory characterizes abelian extensions not as basically characters on this Galois group, but it writes down. But I won't I won't say more about that. But homomorphisms of this full Galois group into here should give you non-abelian class field theory in terms of automorphic representations. The conjecture is that these things should parameterize automorphic representations whose data, that is to say these families CP, are the same as the data that come from the Galois group with its local constituents. I hope that's not too murky. I shouldn't say too many things at the same time. But the Langlands group is a hypothetical locally compact group which comes with homomorphisms into these progressively smaller groups. And I'll just say that it's a hypothetical group that would classify all. So this would have to do with all automorphic representations. The automorphic representations of any quasi-split. Group G over F. Well, it's not going to classify them in a one-to-one correspondence, but rather it would divide them into packets, into global packets, I phi, parametrized. So these packets would be parametrized by L homomorphisms. Phi from, I have a note to myself here, phi from LF into GL, G hat. Okay, so we've defined the L group as the semi-direct product of this connected complex dual group with either the full Galois group or a finite Galois group, and it depends what you want to do with it, but the most general way is to put in the full Galois group, and actually there's a slightly more general thing you could even do with that. You could even put in the Weil group here, the total Weil group, and this is the point of view that's these days typically adopted. The point with the global Weil group, it projects onto the Galois group, and it's the Galois group, or even a finite quotient of the Galois group, that has an action for a quasi-split group that has an action on G hat. So this acts on here through some finite quotient of not just the Weil group, but of the Galois group under this mapping, and usually not a terribly large finite quotient, maybe with a quadratic extension of F, or possibly a larger extension, maybe in the case of D4, there's a larger extension that comes into that. But in any case, let's not worry about these details. The point is, if this is concrete, then these things should be concrete, and you'd still be left with the problem of figuring out these packets. But in the case of GLN, for example, the packets are all singletons, that they're parameterized by homomorphisms of this. Into GLN as a split group, you do not need the action of the Galois group on it, and so you would be enough to consider homomorphisms of this into G hat, which for GLN is GLNC. So in other words, n-dimensional representations of this group. So the packets in that case are singletons. For a more general group, these consist of multiple representations. And then part of the theory that came later would be to classify how the packets themselves, how the representations occurred in the packets themselves. I'll say a little bit more about that later. So in any case, that's what we're looking for, the Langlands group. Okay, so these groups here already have analogs for the local completions. So this is hypothetical. These decidedly are not. This goes back to they. When was that? Does anybody know? Was it 1950s or was it later? Might have been later. Anyway, they defined these things after immersing himself in abelian class field theory, and they are very natural objects. So these are decidedly not hypothetical. They're a well-earned place in number theory. But in any case, these groups, even the hypothetical Langlands group, they already have analogs for local fields. FB. This would be the Galois group. The analog of the Galois group for the local field would be just the Galois group of the algebraic closure, or an algebraic closure of F of the local group FV. And so these come with embeddings. L of FV, LF, WFV. These would embed in the global V group and the Galois group. The algebraic closure of FV over itself, this would embed in the global Galois group. And so these are surjective mappings down here. So all of this is known except this. This is much bigger than everything else, and this is the thing that's hypothetical. So this group, so these are things that they defined, and of course these are our Galois groups. This thing was introduced, a version of this thing was introduced by Deligne when he realized that for the kind of questions Langlands was asking about the local V group, how it is supposed to classify representations, local representations of the group GFP or FV. That's what question 6 of Langlands asked. And Deligne pointed out, well, actually, this is not quite good enough to classify those representations. And he introduced something a little bit bigger, which got the name of the V-Deligne group. It's a little bit bigger than this. Langlands had again, in his Corvallis article, he had a better way of saying what the V-Deligne group was. And it is as follows. LFV is WFV if V is Archimedean, and it is WFV, a direct product with SU2 if V is discrete, p-adic. I hesitate to mention this because I should think about it carefully before I pop off about it. But this is like, if we think of a global field as like a surface, and we think an algebraic curve, let's say, and we think of these completions as points on the algebraic curve, then this thing comes from, I shouldn't be talking about this, I need to think about it before I say stupid things, but this is meant to be the monodromy. This is supposed to be the p-adic analog in the arithmetic case of monodromy. There's something entirely different, which I won't be talking about at all. There's also a group in which you take LF and you take its direct product with SL2, or either SU2 or SL2, whichever you prefer. And this corresponds to the Lefschetz hyperplane section. And so if you're really, so for motives, we don't want to put that in. This motives are things that have a given weight. This group, this larger group, is what you would use if you wanted to describe the cohomology of an actual variety in its different pieces, because this thing keeps track of the weights of the Lefschetz hyperplane section. And but if, I hope I'm not saying too much, but if you're talking about homomorphisms of this group into the L group, then you're talking about algebraic varieties. But the local version, if you took LV cross SL2, that is to say the local version of this thing, well, this LV is supposed to be equal to to the V group of FV cross S. So homomorphisms from SL2 or SU2 are basically the same thing. So well, let's put SU2 there. And then this is SU2. And you got another SU2 there. So local representations correspond to homomorphisms of this larger local group with two SU2s. And so this is supposed to correspond to the Lefschetz hyperplane section. This is supposed to correspond to a monodromy operator. And the interchange of these two things corresponds to a kind of duality, I guess, which you guys, some of you guys know better than me. I guess it exists in physics in many different guises. But this corresponds to a kind of duality whose representation theoretic version that applies just to this is known as Aubert duality. But it's, I'm told that this is related to mirror symmetry and various things which I shouldn't even be mentioning due to lack of knowledge about them. But this does play a role in some aspects of the theory. But right now, we're not thinking about, we're thinking only about automorphic representations. We're not thinking about the cohomology, the full cohomology of an algebraic variety, where you'd want to consider the hyperplane section that changes the weights. You want to consider that all together. So, so here's, I just mentioned that you'd see a little bit of it in this local Langlands group, this corresponding in a natural way to an analog of monodromy. But in any case, these things, these embeddings are defined up to conjugacy. The local Galois group is a conjugacy class of subgroups of the global Galois group. Okay. All right. So now let's talk about so the global Langlands group is hypothetical, and so what I want to describe is a conjectural or a candidate for LF. And it really is, it seems quite natural. There's a couple of things that I have to think further about, and I hope they correct. I hope they fall into place. Even though this has been around, I haven't really thought about it too much in in recent years, but it's, it's important, I think, given all the other things that are happening in this area. It's important to consider it at this time. So there's two ingredients that go into the construction of this. One is an indexing set. Which I will write as C of F. And two, for any C in C of F, a short exact sequence one to KF to LC to the global V group to 1. So it's an extension of the global V group by a compact simply connected group KC. So I have to describe these things. So what is the indexing set? So actually these things are actually pretty simple. If G over F is quasi-split, simple. So it's a simple group. I don't mean absolutely simple. I mean simple just as a group over F. So simple. So it's quasi-split, simple, and simply connected. I'm restricting myself now to just to set up this indexing set. I'm restricting myself to these subgroups, to these particular groups over F. Let me write C. So I defined, before I talked about C of G, these families of conjugacy classes parameterized by primes. So a bunch of families parameterized by automorphic representations. I defined that earlier. So this afternoon, I guess. So let this be the set of C in C aught of G. So this is the set that I defined this morning. This is basically just the set of families C, families C, which represent a bunch of semi-simple conjugacy classes CP, and which are in turn parameterized by automorphic representations of G. I'm going to want to talk about a subset of that. These are the set, let this be the set of C here, such that, so this is an important condition that I want to put on them. We've talked about, this morning, I defined the L function of anything here attached to a representation R of the L group. So I would ask that the order at S equals 1 of this L function that we defined this morning, S, C, R, this would be for any representation. So I'll write it down in a moment, but I'm talking about representations R of the L group. And I'm asking here, I'm limiting this collection of families to families for which this L function has order at S equals 1 equal to the multiplicity of the trivial one-dimensional representation of the L group. This is the multiplicity, this thing here is the multiplicity of the trivial representation in R. Where for every, I want this to be true for every representation R, GL, into any general linear group for any n, or for all n. So this thing is going to have poles. This thing here is going to be at least as big as this. And if you choose something that comes by functoriality from a smaller group, this thing, there are going to be some R here for which this is bigger than this. I am asking that for all families, for all representations, I would ask, all representations R, I would ask that this be no bigger than this. So this is an aside. This is the same. as asking that C is primitive for G. In other words, that asking that C is not a functorial image, a proper functorial image of from any so rho prime C prime for some proper group, proper in the sense that its L group is properly contained in the L group of G for some G prime and C prime in C automorphic of G prime. So if you look back at the definition of functoriality, there's going to be all kinds of automorphic representations of G, or rather the data that come from automorphic representations, the C's. There's going to be all kinds of them, many coming from C primes from smaller groups. I want to throw all of those away and consider only the automorphic representations of G that are not functorial images from any smaller group. They're primitive. They occur for G, their occurrence for G is the first time they occur. There's no smaller groups for which they occur in G. And that is not hard to show that that should be equivalent to this condition. And so then I would like then to take so I've got C primitive, and so then define the indexing set. This indexing set CF to be the set of pairs consisting of a group G, which satisfies these conditions, simply connected, quasi-split, and simple over F, and C, in which C is in this restricted set of data, C in C prim of G. Okay, and I want actually to take isomorphism classes of pairs. In other words, so the set of isomorphism classes is not too serious a matter, but isomorphism classes of pairs in the sense that if you have an isomorphism from G to another group, or maybe an isomorphism of G to itself, you could get a different, something different here, but I want to take equivalence classes, relative isomorphism, set of isomorphism classes of pairs. All right, I'm running out of time, but I can just, I think, get this in. Given C, I'll write C for short, but to stand for an element in this indexing set in C of F. Let me write K sub C. It's a compact group. It's supposed to be a compact group up there, and it is let K sub C. It has a very concrete description. It is supposed to be a compact real form of a complex group, essentially the complex dual group. Well, not quite the complex dual group, but the compact real form of the simply connected cover so this would be G hat SC, simply connected cover of, since G itself was simply connected, the dual group is going to be already adjoint. So the simply connected cover G simply connected hat of the already adjoint dual group G hat of G. And then it's possible, and not difficult, but I won't go through this, can then construct a natural short exact sequence one, well, what I wrote down earlier, a compact group there that basically comes from the compact real form, not of the dual group, but of the simply connected cover of the dual group. And then this LC is the group that's given by this short exact sequence. So it's an extension of WF by this compact group. And unlike the case of the L group, which is a semi-direct product of the dual group with the Galois group, this it does not in general split. It's a non-split short exact sequence. It seems to be what's required when people talk about the motivic Galois group as a gerb. This is, I think, where that's coming in. So this is of locally compact groups. So I haven't described how to do that, but it's not hard. And it's in my article. Maybe not that terribly well written.
Is it a cohomology argument, or is it different? The existence of this extension class.
No, I think it's pretty straightforward. Okay. I think it's pretty straightforward. I can brush up on it, and
no, I just wondered.
Yeah. You perhaps see some other version of it. But in any case, I'll go over this again next time I for the next lecture or whenever it's convenient for people here. Both 1 and 2, I want to be clear, they both depend on functoriality. You can't even talk about this if you don't have functoriality, because functoriality gives I mentioned this morning, functoriality gives analytic continuation of these things to the whole plane. And in particular, this then makes sense. You can't do that if you don't have functoriality. And I think you need functoriality plus a little bit more, but if you prove functoriality by, there's some properties that these primitive things should satisfy. And I think that they're very closely related to functoriality. And I think if you prove functoriality by what's known as beyond endoscopy, the strategy of Langlands for using the trace formula to try to prove functoriality, I mean, that in itself being extremely challenging and difficult. But if you can prove functoriality by beyond endoscopy, which seems to be maybe the only others who may be listening might say that I'm wrong in this, but I think beyond endoscopy is probably the only way to prove functoriality. But in any case, what further things are needed for this seem to likely to come out of functoriality, the proof of functoriality. Okay, I'm sorry, I'll just keep you another couple of minutes if you don't mind. I'll just give the final definition. So here's the putative automorphic Galois group. And what it is, it's so you have infinitely many of these short exact sequences parameterized by these families C and G in this set C primitive of G, and you put them all together. And you want to end up with a locally compact group. So all you do is you just define L of F to be the product over all C in C of F of these coverings of the Weil group. But this is supposed to be a fiber product over WF. So WF is not compact, it's locally compact, but it only occurs once in this. It's a fiber product over this large infinite set of groups, but the fibers are all compact groups. So that's going to be locally compact. And so that is the proposed formula for the automorphic Galois, construction of the automorphic Galois group. So I can say more about this. I mean, I'm happy to talk about, I mean, I want to say a little bit more at some point on the origins of Weil groups, because they're an important part of this. I'm happy. Does anybody have any opinions on whether I should go on with this on Friday? There's a little bit more to talk about on Friday, probably one more lecture to talk about how you then get the automorphic Galois group and the future. We hope for some much optimistic future things that we also want. So but all of that should be one lecture. Does anybody have any? I mean, I'm happy to do it anytime. Or if is Friday? Do you want me to do it on Friday? Is Friday okay? Yeah. So I'll finish this on Friday, and then I'll go back to some more prosaic things on the origins of Weil groups.
First time